I left all of my homework up on Mountain Campus. I'm going to run up and get it right after class, and then I'll bring it back down.
Yep.
I'm so sorry.
That's okay. No big deal. No big deal. That's right. Yeah, me, Peggy, and Mark should be up there. Walk around. Yeah, now it's going to be pouring all day Sunday. So Saturday it should be okay. But yeah, like 2 inches. Like it's a tropical storm that's coming through. Yeah, if you have homework, I'll take some homework.
We had like a pop.
Yeah, I was going to say.
It was like 1865. What's moved out from the last year? What state was she born What about where did environmental science used to be?
We used to be over in the psychology building.
Oh, and experience.
Yeah, I'm thinking, I know around the top is
I used to West
Whenever you have like the always
It was just an extra.
All right, so today we're going to start chapter 7, which is the longest chapter that we'll cover. It's kinetics and inhibition, which is a longer chapter. If you're in lab, you're fairly smart on this already. But don't worry, we're going to go over it in great detail. All right, so the first thing that we're going to talk about in terms of this chapter is just a quick reminder that structure and mechanism tells us a lot about the enzyme's function, right? So everything we did in chapter 6, what's in the active site, what's going on, like how does it bind both mechanically and electrostatically. But structure and mechanism alone cannot tell us how fast the reaction is. Structure and mechanism cannot tell us how well the enzyme recognizes different substrates. And finally, structure and mechanism cannot tell us how the activity is affected by other substances. So, to fully describe, so to fully describe an enzyme, we have to not only know its structure and mechanism, which was everything we just did in chapter 6. But we also must fully quantify catalytic power. How fast and how well does the enzyme work? We also have to fully quantify substrate affinity. And finally, we have to fully quantify response to inhibitors. Which, those three things is the study of kinetics. So kinetics will tell us catalytic power of an enzyme, it will tell us substrate affinity, and then kinetics can tell us about how an enzyme responds to an inhibitor. So we're going to work our way through all of those topics, starting with a very basic review of kinetics. I'll assume no one in here knows anything about kinetics and work our way forward, which, based on what I've asked you before, means you've probably forgotten Chem 109. So we'll work our way back through Chem 109 up to the present. Everyone have all this? Almost. Okay, so we'll start all the way back here with reaction kinetics. So let's say I have a reaction that substrates go into products, S go into P. The progress of this reaction is expressed as a velocity. So we can describe this reaction in one of two ways. Either it's the rate of disappearance of S, or it's the rate of appearance of P. Everybody would agree with that, right? You can either measure how fast you're using up your starting material, or you can measure how fast you are making your product. And specifically, we'll call these concentrations. Right, when I put like those square brackets around it, means concentration. So, if I want to describe what I just wrote in English as a mathematical formula, I would use our little v that's kind of italic and tipped over to the side. That stands for velocity. So the rate of disappearance of substrate, what does rate require for me to measure it? Time, excellent, everyone all at once, very good, time. I have to have some period of time that I am measuring. So, put that down here, velocity. Rates, all these rates. Require some sort of time frame, like 10 seconds, 1 minute, 20 minutes, something, right? You have to start and stop the experiment. You have to know how long it took. So, look at that, it almost looks like calculus. What does the little tiny d mean? It means change in, right? In general, like if it's a little d, it's a little change. If I made it a capital D, it's actually a triangle because it's Greek, right? So delta. Delta is big change. These are little changes, so they're little d's. Look at that, all your classes integrating together. When you get to be juniors and seniors, all your classes kind of mesh together in that way. There is a reason I have you take all those classes before you get here, so they all kind of come together. All right, so I have, I tell my freshmen all the time, pay attention, because you'll need this in a year or two. They never believe me, and then you get here, I'm like, see, I told you. All right, so so I'm saying change in substrate concentration over a change in time. Why do I have it as a negative?
Because you're disappearing.
It's disappearing, right? You're looking at the disappearance of substrate concentration over a change in time. So if that's the disappearance of substrate over time, I could also measure the appearance of P. Why is this one a positive sign? I didn't write the positive, that's assumed. Right, it's appearing. Okay. So far, everybody good? I haven't blown anybody out of the water in the first 10 minutes? Good. Does that look familiar at all? No? Okay. Mental note, when I teach Chem 109 next semester, I'll make a bigger deal out of this. So, reaction kinetics, continued. When the enzyme concentration, oh, that should be held, just kidding, held constant, the reaction velocity will vary with A. I guess in the previous example I had it as S. So to be self-consistent, we'll make it S. So, if I have a constant concentration of enzyme in my reaction, how fast the reaction goes varies on how much substrate it has to work with. So far that sounds good? So far intuitively makes sense. If I have more substrate with a known amount of enzyme, the reaction velocity has to increase. However, if you're looking at the graph, you see that is partially true, right? There's definitely, as substrate concentration increases this way, reaction velocity is increasing that way. So we see that it increases, 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 and then what starts to happen over here? Starts to level off. I spell level. L-E-V-E-L. I kept trying to spell leaves off. That's not right. Levels. Levels off. So the shape of this curve tells us about the way the enzyme and the substrate is interacting. So this was for the previous page. We had S in the presence of enzyme makes P. But based on what we did on Wednesday, we know that that's not exactly the way to best describe this. It is actually, I'm going to call that sort of true. Like, it's not wrong, but there's much more to it. A better description is that the enzyme and the substrate combine to make an enzyme-substrate complex. So that could be some sort of covalent bond. It could be an acid-base catalysis. There's something going on there where the substrate and the enzyme are making a new combination of some sort. And then the enzyme returns to its original state and the new product floats off. So, looking at this curve, we had that the curve increases and then levels off. So at high substrate concentration, I think we'd all agree that a max value of reaction velocity has been reached. Right, so we see a linear increase, and then that's what this line is showing here. There is a maximum reaction velocity that's possible for this combination of enzyme and substrate. So, if I'm at the point where I have high substrate concentration, the substrate is now in excess. So now what is the enzyme? Two words, one starts with an L, one starts with an R. It's the limiting reagent. Look at that, coming back to Chem 108. Man, because we just did limiting reagent in Chem 108. So when we're at high concentration of substrate, now the enzyme is the limiting reagent, which is why we reach a max velocity. You could dump in a ton of substrate, but it can't go any faster because there's no more enzyme available to do the chemistry. We call that point enzyme saturation. I'm gonna go close that door. Somebody's very passionate about what they're talking about there. Okay, so questions on this kind of graph? Feel good about that? Makes sense? Okay. So let's talk about the Michaelis-Menten equation, which we will get there in a little bit. We're going to take some baby steps on our way to the Michaelis-Menten equation. All right, so rate equations can describe chemical reactions. And we're going to take a look at two types of reactions first, just to kind of refresh your memory. Unimolecular reactions and bimolecular reactions. So a unimolecular reaction, how many molecules participate in a unimolecular reaction? 1. Excellent, good prefix reading. So there'd be a reaction like this, like we had before, like S goes to P or A goes to P or however you want to call it. I'm going to use A. So we can describe the rate of this reaction using some math. Oh, you guys all look like frowny face. But until we describe it with math, we can't use a graph. So that's where we're going. We're going to graph this. This chapter is heavy on graphs. Yay! So excited. My absolute favorite chapter. All right. So the same thing we just had, right? So the velocity is related to the disappearance of A over some given time period. We can also describe this in terms you may be more familiar with. Little k makes a reappearance. We're going to work our way up to big K. But little k, oh, you guys do remember this now. Yeah, I hear the groaning. Yeah. Mm-hmm.
Is that lowercase k?
Lowercase k, yeah. When my k's are big, I'll put little caps on them.
Okay.
Try and make them look different. K is our rate constant, and it has units of inverse seconds. Only for unimolecular. So inverse seconds are the units for unimolecular. We'll start working our way up to first order reactions and second order reactions and all that kind of stuff. But so the reaction velocity, this tipped over V, is now proportional to the concentration of A. Right, based on this equation, as A changes value, then that directly affects how B changes value. So a unimolecular reaction that has the equation of this is a first order reaction because it only involves the concentration of one reactant. Okay, good. Okay, let's work our way up then to a bimolecular equation. How many reactants are in the bimolecular reaction? 2. Very good. So bimolecular reaction involves 2 reactants. So it'd be more appropriate to draw it like that. A plus B undergoes some chemical reaction to make one single product. Which means we can then describe this similarly using our rate equation. So I can either look at the disappearance of A, or I can look at the disappearance of B, or I can use a rate constant and monitor both concentrations. And again, little k is our rate constant, but now it has units of inverse molarity, inverse seconds. Because there's an extra concentration factor in here that we'll have to cancel out so that I end up in inverse seconds, molar equals inverse moles per second. Any guesses on what I would call this type of reaction? Second order reaction, that's a good guess. Because it involves 2 reactants. All right, feeling pretty confident on that so far? Moving slow enough? I know it's a Friday. Mountain Day Friday. So it turns out that the Michaelis-Menten equation, which I know you guys are super excited to find out what it is. I keep teasing you. We're not there yet. The Michaelis-Menten equation is a rate equation, which means we have to be able to describe a more complicated reaction than just unimolecular or bimolecular. Because neither one of those exactly involve the enzyme. So we're going to have a slightly different reaction to look at for this. So in the simplest case, we can imagine an enzyme binding to a substrate and then making product, which is what we just had before. And do the arrows that I have, equilibrium and then only one direction. So E plus S is an equilibrium with an enzyme substrate complex, which can only head off to enzyme plus product. So even though this is the simplest case, this reaction is going to have first order and second order processes, each with their own rate constant. So even though this is the simplest way you can draw it, we now have two different types of reactions going on, which means we have several different rate constants we have to be concerned with. So for each of these arrows, I'm going to label them with a different possible rate constant. So I could imagine enzyme plus substrate going to the enzyme substrate complex. I'm going to call that K1, K sub 1. I could imagine the enzyme substrate complex falling apart and returning to its initial enzyme plus substrate. I'm going to call that K minus 1, indicating that it's the opposite of K1. That the minus tells me K1 goes one way, K minus 1 goes the other way. And the other reaction we're going to be concerned about is K2, where that's the enzyme substrate heading to enzyme plus product. So let's take a look at each one of these possible K values. Oh, for simplicity's sake, we assume that the reaction of enzyme plus product converting back to the enzyme substrate complex, we assume it does not happen. That is a huge assumption. But for simplicity's sake, we're going to assume in this case that it is not in equilibrium returning to the enzyme substrate complex. That once it has made the product leaves the enzyme and doesn't re-enter the active site. There will be some cases where that's not exactly true, but in general, we're going to assume that is a true statement. So let's look at K1. So looking at K1, how many reactants are participating in the K1 reaction? 2. If it's 2, then is it first order or second order? Okay. Same. Let's look at K minus 1. K minus 1. How many reactants participate in the K minus 1 reaction? 1. So what is that kind of reaction? First order. And then looking at K2, what kind of reaction is that? It is still first order because it's one thing going to two things. That's still first order. So let's look at which one do I want to do first? I guess I can do any of them. I'll choose K2 because I just wrote that one down. So if we're looking at K2 and I want to write the reaction velocity equation for that, that would be a true statement for K2, that I'm measuring the appearance of product over time, but really I'm measuring the rate constant of that enzyme substrate concentration. Which means now in order to, does that make sense? No? So For all the other reactions, for first order, right, I could write this, or I could write dP over dt. So I'm measuring the appearance of product. But the rate equation is based on the reactant. So I'm writing, I can do that both ways. That would also be true. The disappearance of the enzyme substrate complex. Disappearance is not a good word in this case because the enzyme is not really disappearing. So, anyway. So the reaction velocity for this step is the rate constant K2 plus the concentration of enzyme substrate at any given time, which that is an experimentally tricky thing to measure, right? Because you're trying to measure a concentration of a transition state, which doesn't exist for very long. So we're going to make some specific experimental conditions to try and help us out in this. So we can measure the reaction velocity by choosing specific reaction conditions that help us simplify our calculations. Okay. So we're choosing our experimental conditions because measuring the enzyme substrate complex at a given point is experimentally tricky to figure out. Really the biggest issue is that depends on other rates. It depends on that K1, K minus 1 happening first to get to ES, to then figure out K2. All right, so I'm going to look at this equation, and we're going to walk through how I can figure out this. Okay, that's the thing I'm looking for, right? The concentration, the change in concentration of DES over a change in time. Which is this over here. So that is going to depend on, let's see. All right, so that's the production of ES, or the that's going to depend on, got my color coding right. Our K1 value, which we agreed is a second order reaction, which means it depends on both of the initial reactants. And that describes the formation of the ES complex from S. So that's that first step. Working against us is K minus 1. And that describes the decomposition of the ES back to the S state. And finally, we have to be concerned with making the product, which is a success, but it's a subtraction because it's removing ES complex. So even though it's what you want your reaction to do, it's officially a subtraction because that concentration is decreasing. All right, I'll finish this last slide and we'll take a little break and take a quiz. So that'll be fun, relaxing. It is a nice break. It's in a group. You can stretch, you can walk around the room. All right, this sentence is way up too high. I'm not ready for that sentence yet, so keep it in mind. But I'm not ready to talk about that yet. I didn't leave myself enough space. So let's choose conditions where this concentration of substrate is much greater than concentration of enzyme. What did we talk about like 20 minutes ago that may play into this? Enzyme is now the limiting reagent, and substrate is an excess, which means we know how it should perform. So if enzyme is the limiting reagent, we can predict the concentrations in time, through time. And I'll leave you hanging there saying, but how does that relate to the graph? Oh, yeah, wait till Monday. Very excited. This is one of my favorite graphs. It has 4 different lines. It's color-coded. There's a shaded gray box where excitement happens. That's steady state is happening right in there. We'll get there. Very excited. Big fan of steady state. All right.